So, we will now look into other test methods like carbonation test, which is done, which is a durability related test. Cement, ordinary Portland cement, its reaction with water produces calcium hydroxide, and it has got some alkalis which are present as alkali, sodium oxides and potassium oxide. They are there in the either generally as impurities in the system, but they act as flux also in production of clinker, reducing down the burning temperature. So, some alkali should be there in the, because sodium is readily soluble, sodium potassiums are readily soluble, they are salts or oxides, and they are available in the world plenty like silica. The whole of the ocean is full of sodium chloride, right. So, they are abundantly available. So, you find them everywhere. So, this should be in the cement also you find. So, this sodium and potassium, they are readily soluble. So, they are highly soluble, and calcium hydroxide, which is sparingly soluble, is formed from the production of hydration product of cement. So, this maintains, this actually allows for a higher alkalinity of concrete. So, concrete is generally alkaline, or cement hydrates are alkaline. So, this alkalinity has got a positive side of it. What is it? The reinforcement, the steel, as you know, iron is not a stable material. Iron is not a stable material. It is actually unstable, because it has been produced by expense of energy. You have stable material is iron oxide or iron sulfide. So, it will try to corrode. So, iron will always form oxides, but if the oxide layer is thick and does not allow further oxidation to occur, then I am not worried. That is called a passive layer. In corrosion process is aqueous process. Now, that kind of oxide formation is favored at high pH, which are not detrimental or dangerous to iron. We will not talk about that mechanism of corrosion here. So, that is sometime if I would like to know the potential or risk of rebar corrosion initiation if in terms of its pH. If the pH is high, it is good, corrosion, active corrosion will not occur, there will be a passive layer around the rebar, which will prevent further corrosion. And if it is less alkaline, then I have the chance of active corrosion. Now, when there can be less alkalinity? If the carbon dioxide from the atmosphere reacts with calcium hydroxide, sodium hydroxide, potassium hydroxide, alkalis and calcium hydroxide present in the concrete, they will neutralize it. The alkalinity will be neutralized, carbon dioxide with water forming carbonic acid will finally form calcium carbonate, sodium carbonate, etc. So, alkalinity will be neutralized. That process we call carbonation process. So, we would like to measure the carbonation front penetration into the concrete, how much this carbonation has occurred. This will occur because carbon dioxide is present around 3%, 4% in the atmosphere all the time, and moisture, if it is available, conducive condition is there, reaction of carbon dioxide with the concrete at the surface will occur. We do not mind if it goes, penetrates, but does not reach up to the reinforcement level. It will never occur if there is no moisture. So, carbonation occurs when there is presence of moisture. So, we know carbonation front measurement, therefore, we would like to do. What we do is, you break the concrete, dry and spray phenolphthalein. So, if you spray phenolphthalein, it will spray phenolphthalein. I suppose there is a color showing somewhere, I should have, yes, the color. Spray phenolphthalein, if it turns out to be pink, for example, here it is drilled dry in a cube showing dried drilling, and then phenolphthalein has been spreaded. If the color is pink, it means that its pH is still good enough, it is not carbonated. If it turns out to be colorless, for example, here you can see this, the small little bit drilling, it is colorless, which means that up to small drill, small portion, this is color, this actually the carbonation has occurred. So, phenolphthalein spray is done in order to find out. So, this is carbonation measurement, phenolphthalein spraying is done. So, that is to find out whether how much it is. So, what you do is you break or drill, dry, spray phenolphthalein. If up to some depth you might find that it is colorless, beyond that it is pink color. So, that depth is the depth of carbonation penetration. You can also do X-ray diffraction analysis of the samples to identify whether calcium, drill out, take the powder, do X-ray diffraction. So, you have to actually take a core, slice it off and grind it and do X-ray diffraction to find out calcium carbonate presence is there or calcium hydroxide. There are Fourier transform infrared spectroscopy, FTIR, then TGA thermogravimetric analysis one can do. I might talk about this in connection of fire if the time permits. Thermogravimetric analysis can be done to identify presence of calcium hydroxide or calcium carbonate, etc., etc. So, these are instrumental one, but very commonly done is the phenolphthalein test. So, what we do, as I said, I drill some hole and spray phenolphthalein, and you can see that this color is turning pink, carbonated, uncarbonated, and if surrounding you find that is carbonation is inside, carbonated is pink inside, but somewhere around the surrounding the some depth up to which is a two-dimensional picture not showing properly, up to uncarbonated, carbonated because it is colorless. So, one can visually observe colorless or right, that is how it is. For example, this holes show carbonated, this holes show uncarbonated, sorry, this is carbonated, this is uncarbonated, pink is uncarbonated and white color, same color remaining is actually carbonated. So, the depth of this is known, depth of my drill is known, up to that depth carbonation has occurred, and when I drill further inside I find that carbonation has not occurred. So, depth of carbonation I can find out by simple measurements, right. So, this is how it is done. Here for example, you drill the hole dry, is showing you how you drill the hole dry in the same ones, same. Then one other is finding out chloride, sometime we would like to find out chloride. Now, chlorides are two type, free and bound, because some of the chloride present in concrete can chemically react with tricalcium aluminate or get physically bound. So, what you do is you take sample, grind it into powder, pass it through a specific size sieve, very fine sieves 150 micron or whatever it is, dissolve it in water for half an hour in distilled water, boil it and filter it, right. So, the precipitate you throw out, I mean the one on top you throw out and you take the filtrate, titrate it for chloride. So, you can find out the chloride concentration. So, basically chemically combined, some of the chlorides are chemically combined. For example, tricalcium aluminate in cement reacts with calcium chloride forming this salt called Fredel salts. So, they are chemically combined. So, chemically combined chloride you want to find out, you have to dissolve it in 6 normal nitric acid, concentrated nitric acid. So, I am not interested in telling why higher chemically bound chloride, like they have the positive effect, because chloride is also responsible for corrosion. Like low pH active corrosion can occur, high chloride concentration active corrosion can occur. So, we would like to find out chloride concentration sometime. So, therefore, 6 normal acid soluble is 6 normal nitric acid soluble chloride. So, you dissolve it now in nitric acid, grind the concrete, dissolve it in nitric acid and then you titrate, then you find total chloride. You dissolve it in water, boil it actually for half an hour, then you find out the chloride content by titration, that you call free chloride or water soluble chloride. Then titrate with silver nitrate or mercury nitrate, right. So, these days you do not have to really worry if you have not seen this titration, you have automatic titrator, electrochemical, Carl Fischer titration, another electrochemical process. So, what it does is you pour your material, press the switch and little bit of it should display you the chloride concentration, little bit of inputs you have to give in terms of certain constants and things like that. So, automatically there is a motor which will drop, no pipette burette business. I mean obviously pipette burette is more accurate, but you need skilled person for that. So, if a skilled chemist is doing, because here the person has to actually visualize the color changes going from, because endpoint is decided by change in color. Now, if you are not experienced, you will not be able to judge, like if you have done it in the school days, remember the color changes, it vanishes, shows a color, vanishes, keep on shaking, etc., etc. But the electrochemical automatic titrator, they find it out on their own. Accuracy might be slightly less than visual, but visual needs lot more skilled people. So, anyway, so this titration is done. So, this is another measurement for chloride measurement. The other measurement related to durability is resistivity measurement. Resistivity, because corrosion is an electrochemical process, current passes, so high resistance concrete is better. So, you measure resistivity of concrete by this 4-pole method, 4-probe method, Werner methods actually. So, you have actually, you just place that one onto the concrete. Now, there are 2 probes here spaced at S and 2 more probes spaced at S. Actually, what you do, you pass a current through this, alternating current through this, and measure the voltage in the inner one. Now, the instrument is automatic, you do not have to do much, this is automatic, and it will tell you what is the resistivity of concrete. The formula is something like this: resistivity is given as twice pi, S is the spacing, B over I, twice pi S, where S is the spacing, S into V by I. So, V is the measured voltage across these two, I is the current that you have passed. From that you can derive this, but in this class I am not interested in deriving this. If the resistivity is very low, less than 5000 ohm centimeter, you say that resistivity is low, means current can pass. So, risk of corrosion is high, very high. If the resistivity is very high, more than 20,000, very low, possibility of resistivity, corrosion to occur. So, low risk of corrosion, high risk of corrosion, depending upon the resistivity value. So, what you can do? You can actually measure it over large grid, over a slab, bridge, deck, or building's roof or floor, and then you can plot contours of high resistivity area and low resistivity area. So, you can demarcate the areas of high risk corrosion risk areas and low risk corrosion areas. So, this is what is used for actually demarcating areas of high risk of corrosion and low. You can do further testing, you might even break to see whether actual rusting has occurred or not then, but first you do demarcate this area. So, this is Werner proofs method, the potential between C and D is measured, phi from C D is due to current I entering, this is a current, well this is showing DC, alternating current can be used, there is no problem. A is B is calculated, at current entering at A and B, and calculated that basically one can derive this formula, because current entering spreading, it will go like this, lines, equipotential lines, right, it will spread along this direction. So, actually d phi dr you can actually derive, but I think I for this class I will leave it at this stage. The formula I have given you, it can be shown that delta phi is given by this I, the current entering, rho divided by 2 pi 1 by R 2 minus R 1, and from this one can derive this equation delta phi is equals to I rho by 4 pi A, where A is the spacing, same thing what I have showed earlier, and total delta phi because of two such thing acting will be delta phi 1 plus delta phi 2, which will be measured between the potential difference between C and D, and it works out to be the derivation of this formula is given twice pi A. I said that twice pi S I was saying earlier notation. So, same A, S is same as A actually, delta phi is nothing but V measured V divided by I. So, you can find out by this. Okay, you do not have to do all that, modern machines they will record it and give you a contour after that, because the digital electronics you go on moving it from place to place, record only the coordinates, and later on you will get the contour plot demarcating high resistive areas to low resistive area. Low resistive area means high risk of corrosion, and it might even tell you in red color that there is a high risk of corrosion. Measuring cover. cover depth as well as bar location. Now, this was the very conventional way. You know, if you recollect, how does a transformer work? Transformer will have a magnetic core like this, right? Magnetic core. Transformer will have magnetic core, and then you will have a primary coil here, right, and a secondary coil there. So, as you have alternating current or DI, you know, the change in current is occurring, the magnetic field here will change, and you know, if alternating voltage is supplied through this, magnetic field will change, it will generate actually a magnetic circuit will complete through this magnetic core, and this magnetic flux or magnetic field, you know, change in magnetic field will induce current or potential, you know, the VI. So, generally VI is equals to constant in a transformer, that is what is done. Now, supposing I cut this, take half transformer, this is what is done. So, it is cut, this side secondary is not there, secondary is here, primary is here, but it is cut like this, you know, this portion is not there. So, you have a primary coil and the secondary coil, you pass a current through this, now it will, the magnetic circuit will not be complete if it is air, but if I have a reinforcement bar, then through that magnetic circuit will be complete and you will get a signal in the secondary. So, it is actually half transformer core is cut, the primary is there, secondary is there, but the magnetic circuit will not get completed unless you have a magnetic material. So, you have a rebar, magnetic circuit will get completed and you will get the signal there, that is amplified, and when this is picked, now you can, this is simply a handheld device, you can go on shifting it and see the deflection here. Wherever the deflection is maximum, that means the distance is least, that means you are right on top of the reinforcement bar. You know, on a slab you go on moving it and you measure the, so look at the signal, when the signal is maximum, that means you are right on top of the rebar. So, you can actually locate the rebar and it does it quite accurately. So, in fact, you can get actually complete, you can get like this, you know, locate the rebar, shift it wherever you find peak and along this direction you go on shifting it, you can locate the rebar easily, and today modern system it can actually give you the total diagram of the rebar layout, but it does something more also, not so accurately, because the cover distance, two things are now unknown to me. I have located the rebar, one is unknown is how much is this distance, and second thing unknown is what is the bar diameter. Now, it is related empirically, you know, intensity of this current can be related to the bar diameter and cover depth through empirical relationship. Somewhere it is some cubeth relationships are there, two variables are there. So, accuracy is a problem, but what is normally done is you do a calibration on the same concrete. For example, you know 12 mm bar, you find out for different covers what is the value here or reading here. You can do your own calibration and then go to actual site. So, make same concrete, same cover depth, you vary, do a calibration. Manufacturers provide calibration, accuracy is relatively less, but it locates the bar very accurately, there is no problem about location. Finding out diameter, it gives you calibration curves for various diameter, what is the cover depth, you know, signal, if you get a given signal, given value, the covered for, there will be 3-4 curves here. In fact, in this one the display will be 3-4 curves, right. So, in this curve there will be, in this one the bar diameter, for this bar diameter another bar diameter, and what is the cover depth will be in this scale. So, one can actually measure this. So, these are traditional instruments were there. Today you have digital instrument, some, if it is better, if you can feed your own calibration curves, it can give you, otherwise accuracy is relatively less, but it will give you the good bar layout. So, these instruments are available now, this something like this on wheel and things like that. So, this is what is a ferroscan cover meter, it will go and it will give you something of this sort of bar layout and all you can get, right. diameter is usually a problem, but if you know the diameter, supposing I drill hole and find out the diameter. So, diameter is known, only cover is unknown. Use a calibration to find out cover. But supposing I make a mistake of 1 millimeter, even that can make a difference, because my specification could be 25 mm cover. Actually, it is 25, I measured 23 or 24, 2 millimeter per difference. That itself may not be acceptable to me. So, the accuracy level that is there is not, cover depth problem may come, but layout is very easily found out, and you can avoid location of using this instrument, avoid locations for drilling core. You do not want to drill through the rebar. So, you identify those, do not want to do rebar ultrasonic test through rebar. So, first find out the rebar locations and then do other tests where rebar can interfere with your test results. So, that is cover meter. But today you can have impulse rudder techniques. Here the interpretation is the problem, you must be an expert to do an interpretation. For example, impulse rudder would send signal and images you will get something like this, sort of images you will get if there is a rebar. So, from the kind of images one can actually find out idea about rebar or whether they have been placed correctly or not. So, impulse rudder, the other technique, one is the magnetic type, others is the impulse rudder type, and something like this it can locate. For example, if you have a poor bar detailing, what does rudder do? Signal is sent and it is reflected back, and you trace the time of arrival of the reflected reflected signal. From that you can find out the distance. So, if this was your bar layout, the impulse rudder signal would come something like this. So, you must know how to do an interpretation there, red colored, blue colored and all that. This is actually for this. So, somebody has to be trained, the trained person can do this, but this can give you better idea if you know if the properly interpretation is done, it can give you all the idea. So, this is how we can find out cover. First we said that how we find out the cover using conventional cover meters, magnetic type, and this is impulse rudder technique another way. So, you can find out cover. In fact, GPR, as you know, I will come to that. GPR, as you know, it can find out the foundation depth. Depth of foundation you can find out, not profiling you can do. You send a signal through the ground, reflected signal comes back, from the time you can find out. So, actually boundary of the foundations you can find out. Archaeological survey is using this. I know that it was used in that Kedarnath temple after the flood. It's somebody whom I know, he did that actually. So, you have to have that instrument. So, they found out the rock is still intact, foundation on which the temple was built is built on a rock, hard rock, and rock fell down below. So, that is why nothing had happened to the temple. Rest of the recent all hotels and all, they have vanished away, because they are there is hardly any engineered stuff. This was done at the purpose to last for very long time by those people from their empirical knowledge, and this he found out the the rock profile and all that he found out. So, that is what it is. Okay. This test is Halfcell potential test is done again to demarcate the area of high risk corrosion compared to low risk reinforcement corrosion. We have seen resistivity I can use, right. Low resistivity means high risk of corrosion, and Halfcell potential is another one, because corrosion is an electrochemical process. So, by measuring some potential I can say what is my risk of corrosion, particularly if it is chloride induced. It has been used extensively over bridges and buildings. So, the American Society of Testing Material 876 gives you this kind of a setup, where you have got a copper rod which acts as an electrode in a saturated copper sulphate solution. So, you dissolve copper sulphate in distilled water, saturated, and the copper rod is here, and you can see that there is crystals of copper sulphate crystals of copper sulphate, they should be there, ensuring that it is saturated. So, you should have sufficient copper sulphate, and you should be able to see that, so that you ensure that it is saturated, right. And this is sponge in order to make contact with the concrete. Now, this is sponge soaked in soap solution such that electrical contact is built, and here there is a porous plug. So, it is a tube with a bottom open, there is a porous plug through which this copper sulphate solution is actually all moist, all saturated with water. So, this is all conductive. So, this sort of is conductive, and there is a voltmeter here. Usually voltmeter have high resistance, because through the voltmeter current does not pass, it is not supposed to pass, you measure the potential difference. In emitters or current measuring devices, resistance is very low, because current should be passing, and that should cause actually any deflection or any kind of analog or digital display. So, voltmeter resistance is usually very high. This has specifically no current should pass through this, no current should pass through this, right, no current should pass through this ones. So, this is connected to the reinforcement bar. So, you have to expose a reinforcement bar, maybe drill through the concrete and use a crocodile clip or something to connect it, right, crocodile clip or something to connect it, and this is the voltmeter. Now, you measure simply the potential. So, it measures the potential of the bar somewhere there, because this is the nearest distance of the bar, this is conductive. So, potential difference between this. Now, this is what is called a reference electrode, standard reference electrode. So, the electrical potential that would be generated between the copper bar and copper sulphate, and the difference between this is measured by this voltmeter. Standard electrode used in electrochemistry is standard hydrogen electrode, where you have a platinum rod, right, but I think I am not interested in telling you details of an hydrogen electrode. So, you have varieties of reference electrode, and their potential is measured with respect to standard hydrogen electrode, whose potential is assumed to be 0. So, this has got a standard copper sulphate electrode, copper rod, copper sulphate. So, that is called CuSO4 electrode, right. So, that is used, and that has been found to be most suitable. There can be other reference electrode. So, STM suggests this, and you measure the potential, and if it is less than minus negative, more negative than minus 350 millivolt, chance of corrosion is 90%. That is empirically observed by measurement in lot of bridges in North America. So, ASTM has actually classified this. If you find between this potential between minus 200 to minus 350, between this, then you say the chance of corrosion is 50. I mean, it may be corroding, may not be corroding. And if it is more positive than minus 200, that is minus 150 or something, no corrosion is occurring. So, you can actually demarcate the areas of active corrosion from less corrosion here. So, risk of corrosion you can demarcate, right. So, this is how one can actually plot the contour. This is actually by such device which we fabricated ourselves long back. Commercial equipments were not available, and in a slab in IIT where they are demolishing it, we obtained this contour plot. By plotting at different point, take that data, put it in a software those days called Surfer, and which will plot contour for you. So, these lines are, you can see that some will be 227 negative potential line, somewhere you have. So, demarcate the areas of high risk corrosion to low risk corrosion in the slab, but modern instruments might give you something like this, modern instrument might give you something like this. You can see this is the slab. A lot of measurements have been taken, either wheel mounted 5-6 electrode or 5-6 probe together, and finally, you get something of this kind, this kind of plot you get something of this kind. So, modern instruments where there will be some 6 reference electrode or probes simultaneously, you just roll it over, it is wheel mounted. So, you can shift from one place to another. Measure 6 points, shift it, measure another 6 points, and you locate those points digitally. There is a, I mean, it is all microprocessor or computer based. So, you simply input the location according to a coordinate system, and later on it gives you this kind of area. So, where it is red, these are high risk zone, where it is green, low risk zone. So, you can actually determine. So, Halfcell potential mapping can be done in this manner. Other methods are, of course, rate of corrosion measurement. These are other durability test method. So, there are instruments now through which you can find out if corrosion is occurring. So, first you do what, I will come to this method possibly a little bit later, maybe in the next class, but just before that, if you first find out, demarcate the area where the corrosion risk is very high or resistivity is low, then now in those locations you might do corrosion rate measurement, because after all measurement will cost you money. So, first you demarcate high risk area, and then once you have demarcated them, more additional test you do there, and if required even break it and see. So, this is the whole thing, right. So, linear polarization method is one of them, which I will talk about it later on in the next class, right. So, this is a kind of an instrument that would be there, but modern instruments you do not see all those, you just see a probe or something like that. So, you put handheld device, you just place it, something like this, possibly something like this, this I am not going to show right now. I will something like photograph, something like this, something like this, just handheld device, all right. This is not a very robust instrument, but there are robust instrument in fact, one in the laboratory is for field measurement also, but I think I do not have that photograph of that. This is also there in our lab, but there is a no, I do not think I have. So, this is this I will just talk about that in the next class, linear polarization method measurement. There are other methods, but in situ methods they are still debated, there people are developing them. There are AC impedance spectroscopy, colostatic methods, Galba pulse. There are several instruments now available to measure the corrosion rate in actual structure. Now, this is important because a lot of maintenance cost goes with the rebar corrosion, right.